All right, guys, so let's get started. So I think the last thing we did was converting a number from decimal to binary. And then we did. Oh, we did hexadecimal already. Oh, so all this is done. Okay, excellent. Yeah. So do we do these examples then? Yeah. Okay, perfect. All right. So I probably just didn't save the PDF. Okay, representing numbers, positive and negative. Okay, did I show you guys how to represent a certain answer using different numbers of bits? Did that? Okay, perfect. All right. So we're in a good place. Yeah, in fact, too quick because we're going to be done just now.
That's fine. That's fine. Because more like more like what's this like? Oh, we're going to be down.
We'll see how it goes. Okay, the more time for revision we have, the better, I guess. All right. So today we're going to learn, guys, please settle down. All right. So today we're going to learn how to represent negative numbers in binary, because you notice everything we've done so far has been only positive. All right, guys, please settle down. Okay. Guys, there's a lot of space here. Why are you struggling like that? All good, okay. Everyone, find a seat, get comfortable, make yourselves at home, don't be shy. All right, so representing negative numbers in binary, there are two methods to use. The first one is very outdated. It's a simple sign bit. The second one is called 2's complement. Have you guys heard of any of these before? New stuff. Okay, that's good. So it's new stuff. So we'll take it slow. So a simple sign bit, again, is not used today, but for historical reasons, I guess we're going to look at it. And because the next method, which is used today, called 2's complement, it kind of builds up on this. Not exactly, but you'll see what I mean when we get there. Okay, so a simple sign bit is called a simple sign bit because it's very simple and it just assigns one bit to represent the sign of the number. So for example, let's look at this example down here. 59 in binary is given by the string of binary bits right here. Again, we've done that the last time. We can check that at some point. But for now, let's assume that to be true. And using a simple sign bit, we end up breaking the number up as follows. We break it up, so there's 8 bits here. The first 7 will be used to represent the actual number. So the magnitude of the number without worrying about a sign. So I'll write it like this, number. And I'll put 2 lines here to represent magnitude. So it's like an absolute value. So that represents the number without the sign. This last bit here, the 0, that represents the sign of the number. Okay, so let me do that a bit better. The 0 represents, why is that not coming out right? One more try. Let's put that small bracket. So that represents the sign of the number. So if that bit is a 0, then we are dealing with a positive number. If that bit is a 1, we are dealing with a negative number. That's a simple sign bit. The first bit just tells you what the sign is. Okay. So if we're to represent negative 59, for example, which is right here to the right of this number, we notice that these 7 bits right here are exactly the same as they are in the first example. It's exactly the same, right? So that just represents the magnitude of the number, which in this case is just 59. So that represents the number 59. And the first bit is a 1. If the first bit is a 1, it means that we are dealing with a negative number. So this part here represents the sign again. And in this case, because it's 1, it means our final answer here is negative 59. This changes the sign. Yes.
Oh, if we use this here and when we get that one to one the same, how do we know whether it's going to be negative 59 or that whole number, you convert, because you convert that binary to decimal, it gives you 187.
Yeah.
So how do we know whether it's going to be a negative or that is it update or is it like include that also?
Yeah, so that's a good question. Let me repeat that and give you the answer. So guys, I've got a good question here. The question is, when we see something like this with the 1 in front, how do we know if that 1 represents a sign or if it's just one big binary number where that 1 is included in converting to the decimal, right? So the answer is, if we're dealing with the sign bit, sorry, usually we will be told we're dealing with a simple sign bit. And if you are told you're dealing with a simple sign bit, then if it's 8 bits, for example, 7 is for the number and the last is for the sign. Yeah. So you always be told if we're dealing with this. So if you're not told, we can't assume anything. All right. Yeah, and we just have to hope that they always remember to tell us, because we've seen in the first test they do make mistakes. So again, if they make mistakes, I'll have to mark either one right. So you guys don't stress about that. Let me saying this on the video, but I did. What they actually expect us to do is, when I see a mistake in the test, me to then email them, log a ticket, wait another 15 working days, get back to me, then start marking. Okay, anyway, let's try some examples here. Let's see, there's a lot here, so let me not overwork you guys. Let's do the first, let's do 4 of them. You guys a moment to try that. I feel like we've done this already.
Do we know if we have it?
It's someone from this group that asked me about negative numbers, and I feel like it was you guys at some point. You guys asked me about binary representation. Oh, I feel like guys, it fluctuates between different groups and stuff. I don't know. It doesn't matter.
GPS must be going.
He was busy asking all the girls to be his egg for you, sir.
That's good.
Apparently that's a thing now. And the thing got 3 eyes for some reason.
Does it actually really small?
Yeah.
What? Binary number. Yeah, it's not kind of important. So do you have our assignments initially together, especially? Yeah. Together. That's the only meeting.
So they use weird notation in the assignment, like for complement, they put a power C for some reason. Which is different from what we use. You know, we use a bar on top of it. I hate that they ask theory questions as well.
Yeah. I did accounting last year. It was one theory that accounting did.
In high school.
There's basically they ask you about like corporate governance and all that tax community service studies. Understanding for the principles of they have so much more theories like actually but usually just do the statements and
Yeah, I know.
there was so much more theory and actual
That sounds almost like law, I think. That sounds almost like law as a subject. Okay, guys, anyone needs more time? All right, so let's get started. The first two are very straightforward. So obviously we need to convert the numbers into binary, but 1 and -1 are quite straightforward. So you can do the long way if you want to, but it's not necessary, right? We can just see. 1 in binary is just going to be using 8 bits. So it's going to be 0, 0, 0, 4, 5, 6, 7, 8. That's 1 in binary, right? Yes. We just add the appropriate number of zeros to make it 8 bits, and there's a 1 at the end. Okay, and using the same logic, for the second one, I'll rewrite the first thing exactly as it is. I'll start off like that. 3, 5, 6, 7 with a 1. But now the first bit needs to change this. That represents a -1. So the first bit here becomes a 1. Right, so this first one is 1. This second one here is -1. But all I did is flip the first bit. Okay. Yeah. Okay, everyone okay with the first two? Yeah. All good? Okay, perfect. All right, so I'm doing the next one, which is -8. All right, so -8, firstly, we need to convert 8 into a binary number. We forget about the negative for a moment. Just convert 8 into binary. So 8 into binary, we'll use this shorter method, which says 8 divided by 2 gives us 4. So that is 4 with a remainder of 0, right? You guys remember this method? Like the last time? Perfect. All right, so then I'll take 4, divide by 2. So again, 8, guys, some of you might be able to just look at that and convert it to binary in your head. If you can do that, that's okay. If not, use the method. Always be safe if you're not sure. So 4 divided by 2 gives us 2. That's 2 with no remainder. 2 divided by 2 is 1. That is 1 with no remainder. And then we have 1 divided by 2, which is 0.5. That is 0 with a remainder of 1. Okay, so writing this from bottom to top, the answer here is going to be 1, 0, 0, 0. So that's 8 in binary, and that makes sense because if we convert it the other way, that's going to be 2 to the power 0, 1, 2, 3. 2 cubed. 2 cubed is 8, right? So that works out perfectly. Yeah. Okay. So that's converting 8 into binary. So what I've just underlined here is 8 in binary. First thing we need to do is convert this into an 8 with 8 bits, right? Okay, so let me change color for that. So I'll write it like this. 8 in binary is given by 1, 2, 3, 4, 1. These are 8 bits. 4, 5, 6, 7, 8. Yeah. Okay. So it's the same number, just with the appropriate number bits. Okay, so now using the same logic we used the last time, -8 is going to be the same thing except the first bit is now a 1. And now note that this here, to be very specific, is -8 using a simple sign bit. Okay. If we use the next method, which is 2's complement, we'll get a different answer, a more appropriate answer. But anyway, this is for historical reasons we're learning this. Yeah, they surely will. Apparently, some subjects are changing the way they study certain things. Like I know physics, when you study physics, it's very historical. You start by learning about all the old models, and then some people get confused by that, you know. So now what they want to do is change it to learn what actually works, and then after that, yeah.
You go to the past.
Yeah.
We will the past. Okay.
Hey guys, any questions here before I move on? That's all. That's all we need to do. It's called a simple sign bit because it's very simple. Good.
Teaching the second language is native language.
Okay.
English one of the takes second to understand English.
Okay. The Google Translate is warm up. Yeah, yeah. I get you, yeah.
The keyboard is a French keyboard. The other one
Oh.
yeah, the French one. Every time I'm saying that I'm pretty cute instead of A.
Oh. Yeah, no, I get you. It's like when I watch those tutorials in India, pause. Yeah. Okay, so let's see what we are doing now. What's this example? Convert binary with sign bit to decimal. Okay, so it's good to try a few of these. Let me overwork you guys. So let's do the last three. So we're given binary numbers, convert them into the equivalent decimal number. And note that here we are using a simple sign bit. Okay, so that means the first always represents the sign and the next 7 represent the number.
Yeah. So it's like a consistent life. I don't know stage name. Yeah. Oh, yeah. Oh, yeah. The chicken on my. No, the chicken, bro. The mission is all now. So it's just, but it's quite down for them. Yeah, that's why I use it for signing because if you don't, I can't see the font. I can't let the names. I'm not one. Just. For answers. Yes. No, no, no. Because if it's these didn't know the same. And then this one change the system. So this one where like it didn't. You see, because normally you have that where you can put a zero. And you have this the one things. You know something. Good, I this one.
But I think that's not the reason. But they will sign the register. All right, guys, let's get going with these three examples. So again, when you're doing these, the usual way we do these is to write the number using expanded form with these two numbers, right, which we've done the last time. That can be a bit lengthy, but it always works. So usually you can skip the first step. If you get used to it, you can skip the first step. So I'm going to do that. And if I confuse anybody, please let me know. So I'll start with the first one, 101000011. Right, remember the first bit is just a sign bit, so we don't worry about that. We just ignore it. So let me just cut that bit off. Let's just remove it, right? It will be here, but you just ignore it. So using just this part here, I'm going to write it like this. Okay, starting from the right, that will be 2 to the power 0. First bit plus 2 to the 1. That's this bit. 2 squared doesn't exist. 2 to the 3, 2 to the 4 all don't exist. 2 to the 5 is the next one that exists. That's plus 2 to the 5. 2 to the 5 is, I think, 32, if I'm not mistaken. Or is it 64? 35. So it must be 32. Okay. Okay, perfect. So this will become 1 plus 2 plus 32, which gives us 35. 35. Okay. And the sign bit is a 1, which means this must be a negative number. All right, so the final answer will be negative, all right, here, negative 35. That's the final answer. Okay, that's just because of our sign bit here. All right, so the next two are going to be the same number with a different sign. Okay, so the next one is going to be 0, that's the sign bit. And how many ones? 7 ones. 1, 2, 3, 4, 5, 6, 7, which is, it's a nice one because you don't have to skip anything in between. It's 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4 plus 2 to the 5 plus 2 to the 6. Yeah, that's all we would go. And this here is probably easier to just do on the calculator, right, to get an answer. Did anyone do that? 127. 127, thank you. So that's 127. Again, it's probably not too difficult to do it in your heads, but I'm just being safe here. Okay, so that is the second one. Let me label these 1, 2, and 3. So 1 is done here, 2 is done here. The third one is the exact same number that we just dealt with, but with a different sign bit. So the answer for this part is still 127, but then the final answer is negative 127. Just the sign is different. Okay, and today we need to get to this thing called 2's complement. So, okay, but before I do that, is everyone okay with what's happening here? Questions, complaints, no problem. Okay, all are good. All right, so let's see if I can get to this other thing today. Okay, so this is just telling us one of the reasons why a simple sign bit is not a very effective thing. It's because if we have this number here or this number here, they both in maths represent the same number, right? Because this is actually, the one on top is -0, right? It's a 0 with 1 for the sign bit. The one at the bottom is +0. It's 0 with a positive for the sign bit. And both of these two are actually the same thing. Right? It's absolutely the same thing. But now we have two different binary strings to represent the same number, which doesn't exactly make sense. Two different representations for the same number. So that's one of the reasons why we don't use this method, because it's giving us a bit of a contradiction here. So a better way to do this is called 2's complement. And for this, we have to follow a bit of a recipe here. It's a 3-step method to convert something. Okay, so let's read this one time over, then we'll try an example. It's really not too difficult. Okay. The first thing we do is convert the number to binary, but again, we don't use a sign bit here. So we always pretend it is a positive number. Whatever number we're dealing with, even if they say, for example, convert -35 to binary using 2's complement, first you just assume it's positive 35 and convert the number to binary. That's step 1. Step 2 then says invert all the digits. So you change zeros to ones and ones to zeros. Right? You flip all the binary digits of your answer. That's step 2. And step 3 is to add 1 to the result. So we're working with a binary number, so you have to add a binary 1 to the result. Okay, which is not as difficult as it seems. Okay, but again, we'll learn best with an example. So let's try something. Okay, and they give us a bit of a big number to work with. So let's see. Yeah, okay, we can do it. Let's convert -118 to binary. The word binary is missing here. To binary using 2's complement. Okay, so the first one we'll do together. Then I'll give you guys an example. So I guess the first thing according to step 1 is we need to convert 118 to binary. Right, according to step 1, so that we can do. So again, I'm going to just open up the calculator and do this quickly without wasting too much time. It's a big number though, so it's going to take a few steps to do this. Yeah, but anyway, let's just do it. So 118 divided by 2 is probably what, like 59. Let's just double check because I don't trust myself. 59, okay. 59 is no remainder, so it's 59 remainder 0. Okay, so I'm going to just do this quietly because everyone knows how to do this. You guys can do it as well if you want to, or you can just watch what I do. I'm not going to trust my brain for these ones. Okay. Not the same thing. All right, so guys, that's step one. Did you guys all get the same thing here? Perfect. So again, when you come here, you can, if you have a doubt, just check your answer, convert it back and see if you get 118. All right, so that's step one. Step two is to then invert all the digits. Okay. So we invert all the digits. So ones become zeros and zeros become ones. So that will give us 0, 0, 0, 1, 0, 0, 1. Right? Straightforward, just flip everything around. All right, and we can finish this before the break. We're almost done. Okay, so the third step is to now add a binary 1 to this result. So I'll write it down here. 3 is 0, 0, 0, 1, 0, 0, 1 plus a binary 1. So a binary 1 is just going to be 1 with an appropriate number of zeros in front until we have the same number of binary bits that we have here. So let's see how many we have. 1, 2, 3, 4, 5, 6, 7. There's 7 in total, so I'll write it like this. 1, 2, 3, 4, 5, 6 with a 1. So it's the same number of bits that we're dealing with. Okay. So usually we work with a standard number of bits that could be 8, it could be 16, it could be 32. In this case, it's 7 though. There's no restriction here, so it's okay. Unless they give us a restriction, we can work with what we have. Okay, and now we can use our intuition or we can find a method to do this. Adding 1 to a number like this, it relies on the fact of having an idea of how to count in binary, right? So what will happen here is this last one here is kind of like a 9. It's the highest we can go to in binary. So adding 1 to that will convert that to a 10. That's what happens there, right? So that becomes 0, 0, 0, 1, 0, 1, 0. Let me just think for a second here. This looks fine. Did it say using 8 bits or anything? Let me just check. Okay, so everything we did is fine, and this is the right answer. But I think it's more appropriate if we use 8 bits. Right? I think we're supposed to always use 8 bits, even though this is fine, because they didn't tell us in the example. Okay, so maybe let's just make that a rule. Always make your number into the standard number of bits. Let's use 8 in this case. 8 bits, okay. So if I use 8 bits, I'm just going to change things a little bit in the beginning using 8 bits. So for step 1, we would have just added another 0 to make it 8 bits, right? Step 2, that 0 would have become a 1, right? Step 3, I'll just put that 1 here and I'll include 1 more 0 to make the number of bits appropriate. Maybe let's make that 0 look better. It looks terrible. Plus 0. And then the final answer will just have an additional 1 here. Okay, so just note how things changed a little bit here by adding that 1 more 0. Okay. And yeah, so the reason I did that is because even though what we did is correct, we followed the method perfectly. At the end, usually you end up with something that represents a sign bit. So because this is a 1, it's a negative number. So it's not the same as a simple sign bit, but if you just look at the number and if the first bit is a 1, it should indicate to you that it's a negative number, right? But if we have a short number of bits, then that won't happen. Okay, so anyway, we'll look at more detailed examples in a moment. So one thing I wanted to show you guys is how to add 1 in binary if this method here is disturbing you a little bit, if it's not as intuitive as you'd like it to be. There's another way to add 1 in binary. So I'm going to redo step 3 it's a bit of an old-fashioned method, but it always works. Right, so step 3, adding 1 to our number, we can write it like this: 1, 0, 0, 0, 1, 0, 0, 1 plus 0, 0, 0, 0, 0, 0, 0, 1, like the old-fashioned method of adding. Right, and this always works. Somehow this always works. So I'll show you guys though how to do it, because we are dealing with only numbers that can go between 0 and 1. Anything higher than that is not allowed. So here, if we add the 1 and the 1 from the front, we get 10, right? Because we can't go to 2. That doesn't work in binary. So 1 plus 1 gives us 10. Right? You guys okay with that?
Okay.
Yeah, because one is like a 9 in binary. It's the maximum you go to. Okay. Okay, maybe we can write it. There's actually not many possibilities here, so I'll just write them on the side. If I have 0 plus 0, the answer is 0. 0 plus 1, the answer is 1. 1 plus 1, the answer is 10. Those are the only possibilities. Okay. Actually. That's all we have to work with. All right. So once we have that, let's try and work this through one step at a time. 1 plus 1 gives us 10, so we write it as 0 carry 1. Right, just as we would in usual addition. Right? So now it's 1 plus 0 plus 0. Yeah. 1 plus 0 plus 0 is 1. 0 plus 0 is 0. And we have 1, 0, 0, 0, 1, which is the same as the answer we worked out. So this is an easier way to do it, maybe. Yeah, but also just one disclaimer using this method. Sometimes at the end here, you will end up with more bits than what you started with, right? You might end up with, for example, an additional 1 here. If that happens, you just discard the last bit, right? This part here gives you your answer. Anything extra, you just discard it. Okay, that 1 is not actually there, so I'm going to take that out. But maybe we'll look at an example just now where that happens. Okay, and guys, maybe I should give you a break now. And because I took up an additional 2 minutes, you can come back at 2 past 11.
Thank you.
Okay.
Yeah.